Hello and welcome to this tutorial on Weka. Weka is an open source and freely available software package containing a collection of machine learning algorithms. The algorithms present in Weka are all coded in Java and they can be used by calling them from your own Java code. However, Weka also provides a graphical user interface from which the algorithms can directly be applied to datasets. For the programming assignments in the Introduction to Machine Learning course, we will mostly be using Weka in its GUI form. This will allow us to spend more time on understanding how the algorithms we come across in the lectures actually work and how to use them in analyzing data. You can download different versions of Weka for different operating systems from the website of the University of Waikato. This tutorial is mainly aimed at people who have never used Weka before. We will look at some of the basic features and options provided by the software and also do some linear regression experiments to help you in solving the questions in the third assignment. Before we start with Weka, let us create a synthetic data set on which we can then apply linear regression. Since this is just for illustration purposes, we will create a simple one-dimensional data set. We will create this data set using a few lines of Python code. So here we have imported the NumPy package. This statement creates the input data, which ranges from -25 to 100 and consists of 100 data points. Now we'll create the output data, which will have a linear relation with the input. Since we are creating the data set here, we know how the input and the output are related. However, if this data was given to us, then our objective would be to try to learn this relation, that is, the parameters beta 0 equals to 12 and beta 1 equals to 3. As we will see, when this input, that is xy pair, is provided to the linear regression algorithm, it will be able to learn a perfect model. This is because there is no noise in our data. So to make things a bit more challenging, we will add some noise to the output. The variable z is essentially the noise corrupted output, where we used Gaussian noise with parameters 0 and 3. We'll now save this data and apply linear regression on it using Weka. We have saved the data in a text file, so let's have a look. Now Weka uses a specific format for its input. This format is known as ARFF, and we have to add a few bits of information to what is essentially a CSV file to make it suitable for use in Weka. We essentially have to provide three pieces of information. This first one just gives a name to the data, essentially specifying what relation this data is showing. So since we have cooked up this data, we're just giving it the name synthetic. Next, we provide the attribute information. We've used x, y, and z as the names of the three columns and specified the data type as numeric. There are other data types which we will be seeing a little later, such as nominal and string data type. The final piece that has to be provided is the data, which we have already listed. Add data specifies the start of the data. Now we should save this in the ARFF format, that is with the extension .arff. Hopefully this gives you an idea of how to represent data in the ARFF format suitable for use with Weka. Just to recap, you have to provide the relation and attribute information, and the data is listed row-wise, that is each row specifies one data point with the values being separated by commas. We will now open this data in Weka and apply linear regression on it. So this is the opening screen for the Weka application. We will be using Explorer. Right, so this is the start screen for the Explorer application. As you can notice, most of the options are grayed out. This is because we do not have any data selected yet, so let's do that. This is the synthetic data that we had just created, so let's open that. Right, a lot of things to notice here. First of all, at the top we have these tabs which allow us to specify different actions. So the first tab is pre-process, where we can do different pre-processing activities such as normalizing the data, filling in missing values in case the input has missing values, and so on. Under the classify tab are listed all the supervised learning algorithms, that is both classification and regression algorithms, which we'll be looking at soon. The clustering algorithms are listed under the cluster tab, association rule mining algorithms under the associate tab. Under the select attributes tab, we can perform attribute selection activities such as subset selection, PCA, and so on. And finally, visualize allows us to visualize the data. So let's have a look at that. Here we have the scatter plots between each pair of attributes in the data. This allows us to visualize the distribution of the data. For example, if we look at the scatter plot between y and x, we can observe the perfect linear relation between the two variables, since that is how we created the data. However, if we look at the scatter plot between z and x, we can see the effect of adding noise to the output. Getting back to the pre-process tab, here we have the relation information. The name of the relation is synthetic. There are 100 instances and 3 attributes. The attribute window lists out the attributes. We have 3 attributes, x, y, and z. On the right hand side, for the selected attribute, we can view some information. So right now the attribute x is selected, so it has 0% missing data. There are 100 distinct values, with each value being unique. Some basic statistics such as mean, maximum, mean, and standard deviation. And at the bottom we have a histogram. Now let us go ahead and apply linear regression on the data. For our first attempt, we'll use the first 2 columns, that is x and y, and remove the noise corrupted output z. Right, so first we come to the classify tab. Here we have to choose the algorithm, so we will choose functions and linear regression. Note that there is a simple linear regression function which is actually suitable for this specific task because we have only one-dimensional input, but when the dimensionality of the input is more, we need the linear regression function. So let's just use this function. These are the default parameters for the linear regression function. We can change them by clicking here. The first parameter is the attribute selection method. That is the method used to eliminate attributes which do not contribute to the learning of the model. Since we would like to handle this ourselves, we will select no attribute selection. We will not be using the debug mode. The third parameter is eliminate collinear attributes, which essentially allows Weka to identify and remove attributes which have a high correlation. We'll set this to false for now. The final parameter is the value of the regularization parameter. Note that we are using ridge regularization here. So initially we'll keep this to 0, that is, we will not be using any regularization. Having set the parameters of the linear regression algorithm, we now look at the different evaluation options. The first option is to use the training data, that is, we use the training data to build a model and then use the same data to evaluate the model. In case we have a separate data set for testing, that is, a portion of the data which has not been used in training the model, we can supply that here. More commonly, we will be using cross-validation. In cross-validation, we will iteratively partition the training data into testing and training splits. In each iteration, we will train on the training split and evaluate on the testing split. The partition will be done in such a way that each data point will appear in the testing split at least once. The purpose of doing this is to get a robust estimation of the performance of the model. We will be discussing the concept of cross-validation in more detail in upcoming lectures. For now, we can go ahead and use this evaluation method. Note that the number of folds simply indicates the number of iterations and the sizes of each split. Here we have 10 folds, which means we will partition the data and build models 10 times, with each partition being a 90-10 split between training and testing. Finally, the percentage split option allows us to split the training data and keep a portion for testing. Next, this drop-down box allows us to select the output attribute, that is, the attribute which we are trying to predict. With all settings in place, we can execute. The main window displays the results of the execution of the algorithm. Going through the output, we see the linear regression function used with the following parameters. The relation synthetic, on which the filter applied is removing of the column 3. There are 100 instances, 2 attributes, namely x and y. We use 10-fold cross-validation for evaluation, and this is the linear regression model that we obtain. Note that we are able to recover the exact parameter values used in constructing the data. The correlation coefficient is 1. The correlation coefficient specifies the correlation between the predicted output and the actual output. Here it is perfectly correlated, and each error term is 0. Now, for a more meaningful evaluation, we will use the noise corrupted output. So we can recover the column which we deleted by selecting the undo button, and now we will remove the y column. Going back to classify, we'll have all the parameters will leave as same and just execute the algorithm. Note that Weka used the Z attribute for prediction. In general, Weka will use the last attribute listed for prediction or classification. Here we observe the effect of noise in the output variable. The estimated parameters differ from the actual parameters due to the noise. We also observe that the error is no longer 0. Hopefully, you will now be a little comfortable with the Weka interface and the steps involved in performing linear regression on a data set. Up to now, we have worked with a very simple synthetic data set. So next, we will apply regression on a more realistic data set. The UCI machine learning repository is home to a number of real-world data sets. Here you can see the different data sets characterized by the primary tasks they support, the type of data they contain, the area from which the data has been generated, and so on. We will use the abalone dataset for our next experiment. Here you can see the basic information about the dataset, such as the associated tasks, the number of instances, the number of attributes, whether the dataset contains any missing values, and so on. The data description page contains more detailed information. Most importantly, lists out the attributes and their data types. This information will be needed for creating the ARFF input format. This is the raw data, and here we have added the information necessary for the ARFF representation. Note that this dataset contains categorical attributes. For such attributes, we specify their data type by listing all the possible values they can take. In this case, the first attribute can take one of three possible values, m, f, or I. Note also that the last attribute is of integer type, ranging from 1 to 29. Here we have specified it as a numeric attribute, but in case we wanted to consider this as the class label for a classification task, we would have specified it as a categorical attribute. Let's get back to Weka and apply linear regression on this dataset. Here we see the 9 attributes along with the associated information on the right. The first thing to do is to handle the categorical attribute. Recall from the lectures we learned about one-hot encoding. This can be done in the Preprocess tab using an appropriate filter. First of all, we select the attribute, then choose the appropriate filter. This filter comes under the unsupervised attribute folder, and it is the nominal to binary filter. On applying this filter, we observe that from one attribute we have now created 3 attributes, one corresponding to each of the possible values that the original attribute could have taken. Also from the histograms we can see that each of the attribute is now 0, 1, or that is binary variable. We can now apply linear regression on this data set. We will start by using the same parameter values as used previously. We will stick with cross-validation for evaluation and try and predict the rings attribute. Here we observe the results. These are the estimated beta parameters, and below we see the error measures. Now the question here is, can we improve this result? One idea is to apply regularization. However, before applying regularization, we should normalize the data, since ridge regression is not invariant to scale. This can be done in the Preprocess tab by selecting the normalization filter. Note that except for the nominal attributes and the output attribute, each of the other attributes has been normalized to a range between 0 and 1. Now we can try ridge regression. Let's start with a value of 0.5. However, to compare this result, we should apply linear regression on the normalized data. So we will run linear regression again with the ridge parameter set to 0. Here we have the result, running linear regression with regularization parameters set to 0 on the normalized data. Looking at the beta parameters as well as the error values, we notice some slight changes. Especially if we look at the beta parameters for some of the attributes, we see that in the result for ridge regression, the parameter values have shrunk. This is understandable since in ridge regression we are adding a penalty term based on the magnitude of the parameters. We can also observe a slight change in the error terms. By trying out different values of the regularization parameter, we can attempt to improve on the performance. However, trying out parameters manually is not feasible. For this, we will use a meta-learning algorithm called CV parameter selection. Essentially, CV parameter selection will take as input a learning algorithm, a parameter of that algorithm, and a range of values to try out for that parameter. Let's specify these. So first we select the algorithm, which is linear regression. We set its parameters. Notice that the regularization parameter is specified with the letter R. So this will allow us to specify the regularization parameter along with the range. So let's say we want to vary the regularization parameter between 0 and let's say 5. In 50 steps. We'll stick with the same cross-validation evaluation and execute. The result of the execution of the meta-learning algorithm shows the optimal value of the regularization parameter as follows, subject to the range constraints provided by us. The beta parameters and the corresponding error measures are shown here. Comparing this result with the results of the previous two executions, where the regularization parameter was set to 0 and 0.5, we see that there are small changes but nothing drastic. This seems to suggest that regularization doesn't seem to have much effect on this model, or perhaps that we have not found the right range of parameters. In case of the latter, we can run the meta-learning algorithm again and specify a larger range. One very useful technique when searching for the optimal parameters for any learning algorithm is to start with a large range and a large step size. This initial step performs a coarse-grained search over the range of parameter values. Next, we perform a fine-grained search in the vicinity of the value which gave the best results in the previous step. That is, we restrict the range but decrease the step size. We will leave it to you to apply this two-stage parameter search on this dataset. This concludes the tutorial on Weka. We hope that people encountering Weka for the first time will feel a little comfortable with the basic features of the software. In this tutorial, we covered most of the concepts which will be required for the first set of programming assignment questions. In future assignments, we will simply mention the algorithms that need to be used and expect you to apply them on the dataset supplied using Weka. We also encourage you to explore the different algorithms provided in the package as and when we cover them and related ones in class. For this, the UCI machine learning repository is a very good source for data sets that can be used for all kinds of learning experiments.